Welcome back to all my returning students, and a big welcome to our class to all of our new people. For some of you, this lesson may be review, and for some of you, it might be brand new material, so let's get started. All right, so first things first, you're going to need to have your class binder and a pencil handy. If you do not yet have your binder, you will need to access your student Dropbox, and again, if you aren't sure how to do that, that will be discussed in the Grill and Chill. Plus, you can also go to our website, go to all the links, enter this year's password, and it will take you where you need to go. You're going to need access to your preface section of your binder, the syllabus section of your binder, as well as lesson 1. Homework assignment for lesson 1. In order to answer those questions, you're going to have paid attention to little hints that I'm going to drop throughout. Now, in the past, I've asked students to name my favorite movie based on hints that I drop throughout the lesson. But this time, I'm going to be asking you to name my favorite composer. So let's talk for just a minute about how we do grading. So we have a specific weighting pattern for our assignments listed here, and this is also going to be located in the preface section of your binder. We're going to discuss assignments a little bit here, so we need to keep this grading scale in mind for context. So once you have read and skimmed through the syllabus and the preface, turn to the first page of lesson 1. So flip through the pages of lesson 1 and notice any blank spaces. You will often have blank spaces to fill in as part of your weekly assignment. You'll fill in the blanks as you work through each week's lesson while reading or while watching a video, like this one, for example. And these pages will remain in your binder to help you study and prepare for tests. You will usually have a homework assignment to follow for each week's lesson, and on the final page of each lesson, right before each week's lab, you'll find your homework page. This page will show you whether your homework is to be completed through your online portal TeacherEase, which is usually the case, or if it's to be completed on paper and uploaded to your portal or physically handed in. This same exact information is provided on your syllabus and in TeacherEase. There may be some changes to the syllabus throughout the year, but I'll let you know if that happens. In science, we call this kind of repetition of information redundancy. If you haven't already logged into TeacherEase, you'll want to pause and do that now. You should have received an invitation to your TeacherEase portal. So one category of assignments on which you'll be graded is your homework and binder work. This category of assignments is worth 15% of your grade. So I want to discuss this one with you because sometimes it can be a little confusing the way this works. So to receive credit for your binder work, I have to have a reason to believe you've completed it. If you are participating in the class discussion, answering questions, sitting with your binder open, I have reason to believe that you're keeping up with your binder work. At any point, though, I can walk around class, stroll around, look over your shoulder, or check on your work. Most binder work homework, oh, brownie point, I caught it myself. That should say homework binder work, not homework. Assignments will begin with an unrelated, often silly question. There's no way to get it wrong, okay? What happens is when I see that you've answered that question, it triggers me to think about whether or not I have reason to believe you've completed your binder work and then credit you for that work. There's an example of a silly question over here in the screen capture of an assignment, and it's the first question, and it says, what is your most used emoji? So to receive credit for your homework, you have to turn it in as instructed for each assignment and turn it in on time. So your homework and binder work together is worth about 15% of your grade, and it works out to your homework being about 10 of that 15% and your binder work being about 5. The points for each homework binder work assignment will be counted on the day the homework is due. So we may have class on one Tuesday, and then I have to think back to decide whether or not you're going to get binder credit for that Tuesday, but it's usually about 5 or 6 days later when I'm making that grade, putting in that grade. That's why it's important for you to answer the binder work question, because it triggers me to think about you specifically and whether or not you seem to have been participating. Now, aside from just asking you to name my favorite composer, I'm also going to ask you to name at least one work of his that I did not name during this lesson. So you're going to have to really pay attention. Now, those of you who know me know that I'm also a vocalist, and my day-to-day work typically consists of classical or sacred music, but I have a real soft spot for Broadway. My composer is one that happens to have a rather large catalog of Broadway music. On the back of your weekly homework assignment page, you will find an image of Rico. This is our mascot, this little dude here. You'll see him everywhere. If you're new, you haven't seen him before, now you know who he is. So each week you're going to have an opportunity to color him according to a theme and turn him in for a prize. The prize is usually a little piece of candy. So keep on flipping, and at the very end of each lesson section of your homework page, you will find your weekly lab. So sometimes you're going to turn in your lab the following week, and sometimes you're going to complete it in class. Sometimes you're going to turn in an individual lab that you've completed by yourself, and other times your team is going to turn in one assignment as a group. You will be working with a team in lab. We have 4 lab teams, and they will change members every quarter. So now you're going to flip back to your first page of lesson 1. And you're going to notice here that your syllabus entry, which is at the front of your binder behind your preface, is exactly the same as what is on the first page of your lesson. So here are 2 places where you can find your assignments for each week. And then, of course, they're also in your grade book. And this is at the end of every email I send every week too. So again, like I said, we will discuss how to navigate class with much more detail at the Gorilla Chill. So if you can attend, be sure to review the slides that are available in your student Dropbox, as well as the Gorilla Chill assignment in Teacher Ease. So now that you know what to do for class, let's get started with some basic info on science in general. Now, my favorite composer is an American composer who lived and worked in the Northeast for his entire life. He attended Williams College, but his musical influences began as a child because his family was particularly close with that of Oscar Hammerstein III. He began his career doing lyrics predominantly before doing both music and lyrics for Broadway shows.
Rico presents How to Science.
All right, so what is science? Google defines science like this: the intellectual and practical activity encompassing the systematic study of the structure and behavior of the physical and natural world through observation and experiment. That's a mouthful, so let's break it down. Intellectual, let's say mental. Practical, hands-on. Encompassing, let's say surrounding. Systematic, organized. Structure, construction is another way to say that. Behavior, we'll say actions. Physical, we'll say touchable. Natural, we'll say real. Observation, we'll say watching, although it can also be smelling, sensing. Observations are not necessarily visual. It's anything that happens with your 5 senses, or 6 if you want to include proprioception. And then experimental, or experiment, let's say testing. So let's rephrase it. The mental and hands-on activities surrounding the organized study of construction and actions of the touchable and real world through watching and testing. Or more simply, the study of the natural world through knowledge about the natural world that is based on facts learned through observation and experiment. So science is broken down into 3 main branches. You have your formal sciences, which are things like mathematics, logic, and statistics. You have your social sciences, which are things like societies and human behavior. And then you have your natural sciences, which break down mainly into physical science and life science. And life science is things like biology, zoology, ecology, genetics. Physical science includes things such as physics, astronomy, chemistry, and earth science. So what are the big ideas in chemistry? Now, one of the shows for which my favorite composer provided lyrics, probably one of the best known for which he simply provided lyrics, is Gypsy. He also spent much of his life collaborating with 2 men in particular, James Lapine and Harold Prince. So what are the big ideas in chemistry? Well, we have atoms, chemical reactions, and chemical bonding. So scientific theory versus scientific law. Anybody who's ever taken a class with me knows that this is something I feel that is extremely important for you not only to understand, but to understand it so well that you can recite it. And it goes like this: scientific theories versus scientific laws. First, real quick, did you see little Rico spin up in the corner there? It says engrave it for eternity. I try to remember to stick that into any lesson where there's a particular topic on a slide that I think you need to remember forever and ever. It's a big time learn it, not just like learn it as part of this lesson, learn it forever. So when studying science, what's the difference between a theory and a law? A scientific law tells what happens, a fact. A scientific theory tells why it happens, an explanation. So this is important. In this class, we're going to study scientific law and scientific theory. For example, there are multiple theories of origin. This class is a science class, and it's going to be taught from a scientific perspective. Any theories of origin discussed in this class will be scientific theories. Different people hold different personal and religious beliefs, and it's safe to assume that all questions and answers in this class are prefaced with an unvoiced according to scientific theory rather than I personally believe that. Okay, so this is important to remember because it's science class, we're looking at things from a scientific perspective, and all of our answers are coming from a scientific perspective. Your personal or religious beliefs about any topic we're covering, you're free to hold them. Obviously, they're yours. They're personal, but they don't necessarily play into the lessons we have. Why is measurement important? All right, so measurement is important. If you stop and think about it for a bit, you'll realize measurement surrounds you on all sides, and measurements matter. So some things that we measure are length, mass, which is how much matter, weight. Now there's a difference between mass and weight. If you put me in space, my mass will not change, my weight will. Weight is the effect of gravity and mass together. So the effect of gravity on your mass determines your weight, but your mass is how much matter there is, or how much of you there is, or how much of any particular thing there is. Area, which is two-dimensional. Volume, which is three-dimensional. Density, which is how much mass is in a contained space. Time and temperature. In the US, we commonly use the imperial standard or customary system. This is what you're used to, inches, yards, cups, pints, tablespoons, miles. But in science and most other countries, the metric system is most often used. The metric system may seem unfamiliar at first, but it's actually much easier to work with once you understand it. The metric system is base 10, so once you learn the units and the prefixes that kind of tell you how many of those units you're dealing with, it is so much easier because you don't have to do conversions from inches to yards or tablespoons to pints. So this is what metric conversion looks like, and we will be going over this in class and using it fairly frequently this year. So you have a unit, that's right there in the center. Meter is the unit for length, liter for volume, gram is for mass or weight, and then there are the abbreviations for those are right below them. And then you have prefixes that you put ahead of the units that tell you exactly how many of those units you're using. So if you look to the right and to the left, you'll see that all the way to the left, for example, 1 kilo is 1,000 units. So a kilometer, kilometer, is 1,000 meters. A hectometer, or that people don't usually say hectometer, but hectometer. Anyway, that would be 100 meters. Or for example, a decaliter is 10 liters. Now, if we're going to the right from there, they're getting smaller in this case. So a deciliter would be 1/10 of a liter. And a centigram would be 1/10 of a gram. Now, I mean 1/100th of a gram, I'm sorry. And you've probably heard of centimeter before, and that's 1/100th of a meter. So if you take a meter stick, you're going to find 100 centimeters on it. And then you have milli, which is the unit for a thousandth of one of your units. So you'll have like a milligram, which is a thousandth of a gram. So you're dividing by 10 in one direction, multiplying by 10 at the other, which is at the bottom, and we'll practice this. And if you need to remember them, a lot of people do. King Henry died unusually drinking chocolate milk. You may have heard King Henry died Monday drinking chocolate milk. Monday was meter, but it's not always meter. Sometimes it's liter or gram. So King Henry died unusually drinking chocolate milk. So how do you present data like a scientist? Okay, so scientific notation, we will be using this year, and definitely this gets used in chemistry. So scientific notation, real quick, I'll just point out at the bottom there. Sometimes numbers get really, really big or really, really small. So we tend to turn that number into a decimal and take the number of zeros behind it and give it either a negative exponent or positive exponent. And that might not make sense right now out of context, but when we get to it, it'll be better explained and you'll remember that you've seen it before. So data are the information gained from observing and testing an experiment. Data is actually a plural word. Datum is singular. So what's a hypothesis? My favorite composer was often criticized for producing melodies that others called unhummable. But he was also known for being incredibly flexible with the lyrics he used and coming up with crazy rhymes like, I sort of hate to ask it, but do you have a basket? A hypothesis is an idea that can be tested. So here are the requirements for a testable hypothesis. Remember, it's an idea that can be tested. So not every idea is a hypothesis. Like you can have an idea that you want to, paint your house purple. And that's not testable, really. I mean, you can do it, but it's not testable. So here's what it means to be testable. In order to be considered testable, it must be possible to prove that the hypothesis is supported. You can think of it as true, but really the word is supported. Or it must be possible to prove that the hypothesis is rejected or not true. Rejected and supported are the ways to phrase this best. And it must be possible to reproduce the results of a hypothesis. So there's your little engrave it for eternity. Don't ever forget this one. All right, so many scientific hypotheses, which is your plural, are proposed in an if-then format because it's easy to design an experiment to see whether or not a cause and effect relationship exists between the independent, sometimes you'll hear it referred to as manipulated variable, and the dependent or responding variable. And we'll talk about variables in a minute. So what if a hypothesis is supported? So a scientist will make sure that she can repeat her process and replicate her results. Because remember, in order for a hypothesis to be testable, it must be repeatable. So what if your hypothesis is rejected? A scientist will revise his hypothesis and often repeat the experiment. Among some of the more popular works of my favorite composer are shows such as Gypsy, which I mentioned before, but also West Side Story. A funny thing happened on the way to the forum. Anyone can whistle. Do I hear a waltz? A Little Night Music. My all-time favorite show, Sweeney Todd, the Demon Barber of Fleet Street. Also Sunday in the Park with George, Into the Woods. And some lesser known, but fabulous shows all the same, including Bounce, Pacific Overtures, Merrily We Roll Along, and Assassins. So scientific method. Scientific method. So this is how you test your hypothesis. So you have to use this in order, if you're going to think like a scientist, you're going to test your hypothesis, using a scientific method and conduct a controlled experiment. So you can't really think of the scientific method as a linear process, like step A, then step B, then step C, because there are definitely some ways you can make turns along the way, depending upon what sort of results you are getting from your experiment. And we'll be using a lot of scientific method in labs this year, so you'll get to practice it quite a bit. So here are variables. Now I said we would talk a little bit more about variables, so here we go. Your independent variable you can think of as what you change. Your dependent variable is what you observe. And your controlled variable is what you keep the same. So in a controlled experiment is one in which only one variable, the independent variable, is deliberately changed at a time. So I want you to think about an example where, let's see, you have frequent headaches. And you're trying to figure out if there's a particular thing that causes your headaches. Or how about this? No, you're trying to think of a way to get rid of your headaches. What's the best method for getting rid of headaches? So you come up with a hypothesis that resting in a dark room is the best way to get rid of your headaches. So you take yourself into a dark room and you take some Tylenol and you take a cold compress for your head and you lay there in the dark and your headache goes away. Okay. You just added multiple things to your experiment. How do you know if it was the Tylenol or the cold compress or the dark room? You don't know. The only way to determine whether or not it's the dark room is to change only that about your behavior. Go and rest in a dark room only, don't take any medicine, don't put on the cold compress, and then see if things change. So how do we be a good scientist? Well, we're going to engage in arguments using evidence, not emotion, people, evidence, okay? You're going to ask questions, define problems, develop and use models. Models are great. We'll talk about models more this year. Models are a great way to exemplify a topic or a point or a concept that is maybe a little abstract. Like think about solar system models. That's a great way to visualize something that you can't visualize on your own. You got to plan and carry out your investigations, analyze and interpret data. Always analyze and interpret your data. Try and figure out what your data means. You're going to use math and computational thinking, construct explanations, design solutions, obtain, evaluate, and communicate information. And that's part of using models. This is how we be a good scientist. So one way to open your eyes is to ask yourself, what if I had never seen this before? What if I knew I would never see it again? And this is a scientist named Rachel Carson. And her work increased the understanding of environmental dangers of a certain chemical called DDT that used to be used to help get rid of mosquitoes. Mosquitoes carry diseases, so you definitely want to get rid of them in certain situations. But it turned out that this particular very popular chemical was causing damage as well. And thank goodness for Rachel Carson figuring that out. Life is not found in atoms or molecules or genes as such, but in organization, not in symbiosis, but in synthesis. And this is Edwin Grant Conklin, and he pioneered the fields of cellular lineage and embryology. Cellular lineage is like, so you've got maybe an embryo developing and there's only 4 cells. Well, one of those cells is going to become particular body systems. Like one might become the nervous system and a different one might become the digestive system. That's cellular lineage. It's pretty cool, actually. It is not the strongest of the species that survives, nor the most intelligent that survives. It is the one that is most adaptable to change, and this is Darwin. Darwin developed theory of natural selection, and his hobby was breeding fancy pigeons. If you want to see some weird stuff, start Googling Darwin's pigeons. He's less known for the pigeons, but it's one of my favorite facts about him. A lot of people like to say survival of the fittest to sum up the concept of natural selection, but that really does not sum it up properly. Properly, the thing to say is that it's the most adaptable to change that is the one that survives and passes on its genes to the next generation. And then we have, I am among those who think that science has great beauty. A scientist in his laboratory is not only a technician, he's also a child placed before the natural phenomena which impress him like a fairy tale, and that's Marie Curie. So she is known for her discovery and work with radioactive elements, which aided in cancer treatments. She has a fascinating life story as well, and definitely one of my favorites. So settled science. This is another big point. You know, Merrily We Roll Along was recently revived and ran on Broadway with Daniel Radcliffe in one of the title roles. I didn't see it, but I've heard it, and it was pretty darn good. I'd also be amiss if I failed to mention to you that Company ran not too long ago with Neil Patrick Harris in one of the lead roles. That's a fabulous show as well. Lastly, never forget, no matter who says otherwise, science is never settled. Okay, why? Because let me tell you, you're going to hear the science is settled a lot. We hear it when it comes to climate change. We heard it a lot with the COVID pandemic. Science is never settled. Why is this wrong-headed? Okay, I'm going to tell you why. And this year, I'm going to do you the favor of summarizing each of our 3 big points into one little, like a little sound bite or a little chunk that you can keep in your head and maybe memorize a little more easily. So there's our little engrave it for eternity, guys. So this is one of my points to keep forever. So this concept that science is settled is wrong because 1, it presumes science exists in a binary state, that science isn't settled until it crosses some imaginary line after which it's finally settled. On the contrary, science by its very nature is never 100% settled. Science does not exist in a binary state. That's the way to sum up number 1. It's not like it's on or off, right or wrong, black or white. Number 2, another reason. It presumes that poor understanding in one area of science invalidates good understanding in others, and this is not the case. So this one's the wordier one. But its poor or good understanding in one area of science does not validate or invalidate good or poor understanding in another area. Basically, there are some things we know a lot about, and there are some things we do not know a lot about. It doesn't mean that what we know a lot about is somehow less valuable or less true because we don't know a lot about something else. And lastly, the third point, and this is one some of y'all tend to miss this one. So natural science is not about absolute proofs. It never reaches 100% certainty. This is the domain of the formal sciences, which, as you remember from our slide before, was like things like math and logic. Science is about improving our understanding by narrowing uncertainty. Different areas of science are always likely to be understood with varying degrees of confidence, which goes back to point number 2. So the goal of the natural sciences is to narrow uncertainty. So you can just ask these guys because they prove that science wasn't settled. Well, you can't really ask them because they're all dead, but there's Galileo Galilei who proved the sun was the center of our solar system, not the Earth. That's a huge deal because for years and years, the consensus was that the Earth revolved around the sun, and he proved it wrong. Darwin, again, introduced the theory of natural selection, providing the first explanation for the idea of evolution. Evolution, the thought that things change over time, that species change over time, had been around for a long, long time. But it wasn't until Darwin posited the concept that it's the most adaptable, that survive change in the environment and are able to pass on their genes. That concept of natural selection is what provided an explanation for evolution. Lister applied germ theory to create the concept of sterile surgery. If Lister sounds familiar to you, maybe because you've heard of Listerine, which is named for Joseph Lister, and Listerine is obviously antiseptic, kills germs. Prior to Joseph Lister understanding and applying germ theory to things like medicine and surgery, I mean, we're talking like, you use a bone saw on one guy out in the field after his leg's been shot with a musket, and you slice it up, and then you take the same bone saw to the next guy, and then you just leave it in the mud until you're ready to use it again. We can't even think about that these days. I mean, we can't conceptualize that because to us it seems crazy, but prior to him, people really did not think diseases were passed on that way. Wegener. Okay, if you did earth science with me last year, you know Alfred Wegener. Alfred Wegener originated the theory of continental drift. He was able to explain why continents move over, well, not why. He was able to explain that continents move over time. That we used to have Pangaea, which was this big, massive continent, and that continents shifted around and things weren't always in place. And he gave evidence for why this happened. But his theory was not well accepted at the time because he did not provide a mechanism for the theory, which later we learned was plate tectonics, and it has to do with convection heat in the mantle of the Earth moving around our continents. But he wasn't able to provide data for that, so people kind of laughed at him and thought, continents moving, that's silly, that's ridiculous. It's kind of like Darwin came in and he provided the mechanism for evolution, whereas Wegener just said, well, this happens, and he was right, it did happen. And then how about Robert Goddard? He was laughed at for suggesting that we could travel to space using a rocket. And that's kind of funny because now it seems like every day some billionaire is going somewhere in a rocket, or, we do it all the time. We've been doing it since the late 1960s. And here's our guy, Robert Goddard, who suggested it and got laughed at. So who will make the next great discovery? You never know. It could be you. I was terribly sad to learn that my favorite composer had passed away in 2021. Now, he was 91 years old, so he lived a fabulous life, but it kind of broke my heart to know there would be no new music from him ever. Good luck with that assignment.